Schrödinger's work. So in HSC physics, in the last module, in module 8, looking at the quantum mechanical model of the atom, we look at Schrödinger's model. So Erwin Schrödinger, pronounced Schrödinger, was an Austrian-Irish theoretical physicist. So he was born in Austria, raised, and then he moved to Ireland, where he got his citizenship and lived and worked there for the rest of his life. And then he actually went back to Austria later, but anyway. Schrödinger, he built upon Louis de Broglie, the French physicist, built on Louis de Broglie's matter waves, his idea of matter waves, to formulate a new model of the atom. So de Broglie, in 1924, he proposed that particles like electrons can have wave-like properties through the formula lambda is h over p, where p is the momentum, mass times velocity, and h is Planck's constant, a number 6.626 times 10 to the minus 34 joule seconds. And lambda is wavelength given in meters. So electrons can be thought of as being these waves defined by some wavelength lambda with mass and velocity moving in space. So Schrödinger, he took de Broglie's idea of matter waves and he asked, if electrons can behave like waves, like this, how can we then find some mathematical description to describe them, some wave equation? So how did he figure this out? Well, he actually went on a skiing trip up in the Alps, and the story goes he came back and he came up with the idea, miraculously. And he developed what's now known as the Schrödinger equation. I'm going to write a simple expression here. You don't need to know this for the HSC. I'm just going to show you. This is uni level stuff. This is the Schrödinger equation. You can, if you want, learn this if you have a good memory, but there's no need to really for the HSC. Okay, this is called the time-independent version. There's different versions of his equation. Time-independent means there's no time in this expression, and this applies to bound systems like atoms, stable systems that aren't really changing, that aren't moving. H with a hat on top. Okay, this is called the Hamiltonian operator, named after Hamilton, mathematician. Okay, the Hamiltonian operator contains the total energy of the system. Let's say the atom in this case. It's the sum of the kinetic energy and the potential energy. Psi, capital Psi, this Greek symbol here, is known as the wave function. Okay, and this describes what's known as the probability amplitude of the particle, of the electron, let's say. And E is the energy of the particle, the electron. So Schrödinger thought, let's look at a simple atom. Let's say got the positive nucleus here. Schrödinger thought, so unlike de Broglie, who thought that the atom looked like this, let me draw something like this. Schrödinger thought that the electron was like a cloud, a probability wave. So these dots, where these dots are really dense, really dark, that's not where most of the electron is. That's where the electron is most likely to be. Okay, let's say a 99% chance. And it makes sense if you really think about it. There's a really high chance of finding the electron near the nucleus, because think of electrons as being negatively charged, protons as positively charged, and they attract. Where the dots are less dense, that's where the electron is less likely to be found. Let's say 1%. So Schrödinger took this idea of probability quite literally, and he said that there's no more certainty in physics, in the atomic models. We can only have probabilities, likelihoods. You can only say that an electron might be here in this particular part of space. That's all you can say. Now, really bizarre, but he was actually right. This has been tested over and over again in experiments. In fact, this is what makes devices like phones work, touchscreen devices even. You can look this up on Google. There are things called quantum tunneling composites that are used in touchscreens. Okay, QTCs. These use basically the Schrödinger model. But the electron is now a probability wave. Unlike De Broglie, who said that electrons are just waves, Schrödinger said no, they're not just any type of wave, they're probability waves. So think of the wave function psi as being like a map that tells us where the electron is most likely to be. And E is the energy of the electron, and H with a hat on top, this is like a special mathematical tool that adds up all the energies. Okay, how fast the electron's moving, that's kinetic energy, and where it is, that's a potential energy. So in other words, this equation tells you if you use this mathematical tool, this operator called H hat, if you use this H hat on the wave psi, this tells you the total energy of the system E of the electron. If you solve this equation is very important because if you solve it, you get the shapes of these waves. You get the shapes of orbitals. So you don't have orbits anymore. You get orbitals. So unlike in junior science where you have the Bohr model, look at these orbits, these lines. Orbitals come in like 3D shapes, different shapes and sizes. And you also get the allowed energy levels. Okay, Schrödinger's equation is very powerful because you can conceptualize and visualize the shapes of these orbitals, these three-dimensional orbits, and the allowed energy levels. You can actually calculate the energy levels, unlike in Bohr's model. So n equals 1, n equals 2, etc. The Schrödinger's equation is more powerful. Okay, and it shows you why atoms give off particular colors of light. And using his equation, Schrödinger showed that only certain wave functions, psi, and hence energy levels, were allowed for the electron in the hydrogen atom. Okay, the same quantized levels that Bohr proposed, but now derived from first principles, from pure mathematics using his wave theory. Okay, so only certain psi's, wave functions, and therefore energy levels n. Okay, remember the quantum number n means energy level. So only specific wave functions were allowed for the electron in a hydrogen atom. So here's the hydrogen atom, the proton in the center, the nucleus. Only particular orbitals, let's say like this, something like this, I don't know if I can draw it. So he actually showed using rigorous mathematics, yes, this is how atoms look like, electrons, this is how they work, and what we see in the lab indeed corresponds to the theory that Schrödinger proposed.